Today we're going to look at the double angle identities for sine and cosine. For example, we want to figure out how to derive the sine of 2 theta. And we're going to start, or we're going to use the angle sum identity to do that. Because if you think about the sine of 2 theta, that's actually the same as the sine of theta plus theta. So basically, I can use the angle sum identity, but instead of x and y, they're going to be the same thing. They're both going to be theta. So here's what that looks like. The sine of theta plus theta, because that's 2 theta, that's going to be equal to the sine of theta, cosine of theta, plus the cosine of theta, sine of theta. Well, I basically have the same term twice because I can just rearrange these. The commutative property lets me do that. So I have 2 of the sine theta, cosine thetas when I add them together. So in the end, here's my identity. The sine of 2 theta is equal to 2 sine theta, cosine theta. And again, if you can start with the angle sum identities, you can get to this one without necessarily having to memorize it, because it's pretty quick to deduce from the angle sum identities. So there's the first one, and the second one we're going to look at is the cosine of 2 theta. So we're going to do a similar process here. The cosine of 2 theta, that's the same as the cosine of theta plus theta. So using that identity, it's the cosine of theta times the cosine of theta minus sine of theta, sine theta. So the shortened version of this, the cosine of 2 theta, the double angle identity for cosine, is cosine squared, that's a 2, minus sine squared. That's one version of the cosine of 2 theta. Now, because we have a cosine squared and a sine squared, there's 2 other ways to write this, because remember, just as a side bubble, the Pythagorean identities, we have an expression for cosine squared, and that's equal to 1 minus sine squared. And sine squared is equal to 1 minus cosine squared. So we can substitute those things in and come up with 2 other expressions. And so that one's going to look like if I replace the cosine with 1 minus sine squared. So let's replace this one first. And I have cosine of 2 theta is equal to 1 minus sine squared minus sine squared. So I have 2 of the same things. I'm going to combine them. So here's the second way to write the double angle identity for cosine. Cosine of 2 theta is equal to 1 minus 2 sine squared of theta. So there's the second way to write that. So the third way to write this identity is to replace the sine squared with 1 minus cosine squared. So here's what this looks like. Cosine of 2 theta is equal to cosine squared minus, in parentheses, 1 minus cosine squared. So if I take the negative 1 here and distribute into the parentheses, I'm going to have a minus 1, and I'm going to have a positive cosine squared, which looks like this. Cosine of 2 theta is equal to cosine squared minus 1 plus cosine squared theta. So here's the third way to write this. Cosine of 2 theta is equal to 2 cosine squared of theta minus 1. Please don't confuse the double angle identity with the Pythagorean identity, because for cosine of 2 theta, we have a subtraction sign in the middle. The Pythagorean identity is cosine squared plus sine squared. So there's a difference there. Don't confuse them. Alright, so we're going to work an example of how we use this, or how we evaluate. It's pretty basic, really. Given sine of theta is negative 3 over 4, so I have the ratio, and I have this information here. 3 pi over 2 is less than theta, which is less than 2 pi. I want to evaluate the sine of 2 theta. Again, we're not going to use our calculators. We're going to work strictly with ratios. So if I think about this, and I'm not going to double negative 3 over 4. That's not how we do this. First of all, the quadrant. This tells me that I'm in quadrant 4, which is going to affect my signs when I do my identity. So the sine of 2 theta, the identity that we use is 2 sine of theta cosine of theta. So I need ratios for sine of theta and for cosine of theta. I already have sine of theta, it's negative 3 over 4. So when I evaluate this, I'm going to replace the sine of theta with negative 3 over 4, and now I need a ratio for cosine. It's quadrant 4, which means he's going to be positive. So I need to create my right triangle, and here's theta. And if sine is 3 over 4, that means 3 is opposite, 4 is the hypotenuse. And I need to use Pythagorean theorem to come up with this side's going to be radical 7. So in the end, my ratio over here is going to be radical 7 over 4. And then I just multiply through. One error that I see a lot in pre-calculus, unfortunately, is the 2. A lot of kids will take this 2 and multiply the top, the numerator, and the denominator by it. Please don't do that. If you need to, put it over 1. But it's 2 times negative 3 times radical 7. So the numerator is going to be negative 6 radical 7 all over 16. And from there, it can reduce down. So I can reduce each by 2, and my final answer is negative 3 radical 7 over 8. That's the sine of 2 theta. So now let's evaluate the cosine of 2 theta in the same problem. So we start theta's in quadrant 4, and we already have the ratios for the sine and the cosine. So if I use my identity, the cosine of 2 theta, you can use one of the three. We can use cosine squared of theta minus sine squared of theta. So if I substitute in, I have radical 7 over 4, and I'm squaring that, minus negative 3 over 4, and I'm squaring that. Remember, when you square negative, you're going to get a positive. So this ends up being 7 over 16 minus 9 over 16, and that should leave you with negative 2 over 16. Reduced down, it's negative 1 over 8. Now that should make sense. If theta is in quadrant 4 and you're doubling it, it's going to probably put it in a quadrant where the cosine is negative. So the cosine ends up being negative 1/8. And in class we'll talk about the double angle for tangent, and we'll work on a couple other things using these identities.